the starting point for the ensemble theory. So we talk about the phase space. So this is just representation of the phase space, because even for very easy case, the phase space is 6-dimensional because of scale coordinate and 3 moment. So we can present the real phase space only for 1-dimensional system. So this is just read it as a phase space Pi and Qi, or just Pi or Qi is just representation for the phase space of phase portrait, and this index is running from 1 to 3n. N is the number of the body. So we have I told you we have a collection of representation in the phase space, like the separate island. So they are represented some number of the particles they are collected together. So we have some kind of the island here. So each one have a density. So for each point of the phase space, you can define the rho as a Qi and the Pi as a density of the different representations. And but this is very similar to the case of quantum mechanics. In quantum mechanics, from the Schrödinger equation, you can find the wave functions, but wave function as a single object doesn't have any physical meaning. So when it becomes meaningful is that when you consider the square of the side. So that's called the density. So this is like that. So rho doesn't sense too much from the physical point of the view. It appears in the Liouville theorem, but it doesn't sense more to the physics. So we define the Qi Pi d3n Q d3n pair as the probability, or as a density of representation in domain or in the range Qi and Qi plus delta Qi and Pi plus delta Pi. So the total number of the, and this is actually dn dqn. This is a volume element in phase space. This is a hyperdimensional volume, or n-ball volume, 2n-ball volume element in the phase space. So the Liouville theorem statement is that the total derivative of the rho, which is given by that, is equal. So T. So this is just non-relativistic variant of the Liouville theorem, because here the time is appear here as the parameter for the evaluations, and you have a Poisson bracket as a part of the spatial change in the function rho. So I wanted to prove this theorem, but I will use the very elementary techniques to prove that. So this Poisson bracket, rho and the edge, versus the Q and the pair Poisson bracket, is given as a summation over the coordinate from the H from the pair I, or pair I. This is we call it Poisson bracket. So this 3n is the number of the degree of the freedom of the system multiplied to the number of the particles. So f multiplied to n, and in your case f is 3, but maybe you have a one-dimensional gas, so f will be 1. Or you have a two-dimensional gas, like graphene in condensed matter. So this is just the surface, so you have a f2. But for the normal gas, this is f2. So to prove this equation, I want to back the very fundamental physics, heat transfer. This is the idea came from here. We have something called continuity equation. This equation is the equation which we repeated several times in the fluid dynamics, as well as electromagnetism, and also in quantum mechanics. In quantum mechanics also you have the continuity equations. Continuity equation say that always you have something like that. This del is the generalized gradient operator. So this is some kind of the spatial derivative. I mean, this is a derivative with respect to the normal coordinate like x1, x2, if you have more, or y1, y2. It depends to how many dimensions your system has. And t is the symbol for the time. And J is the something which call it the current, flux. So if you understand the proof of this theorem, so you can easily understand the proof of the Liouville theorem. How we prove that? So in heat transfer, the idea is that the flux of heat is because of the change in the temperature. Or otherwise, you have another version of that. You say that electric current is made in the system because you have a time change in the charge density. Change in charge density. Or you can repeat that for the mass or anything else. So we considered a region of the space with the volume omega. So the density at the beginning is rho, so it can be the density of the charge, it can be density mass, even the quantum mechanical density, probability for anything. This is a general proof. So you have a rho, and you just consider a small transfer phenomena from this volume to the outside or to the inside. The change in the rho, grown partial derivative of that. If you want to have a flow to the outside, so partial derivative of the rho with respect to the time should decrease. Because the density should decrease. This decrease make a flow for you. So you have a flow of flux of anything, electric current or even the fluid and everything. You understand me? This is the logic which I use is that to unify all the phenomena in one equation. All the phenomena for me is the same. Fluid dynamic or electromagnetics or quantum mechanics, they have the same formulation, at least in this level for Liouville theorem. For me, doesn't make any sense, change that this is a heat or this is an electric current or this is anything else. So the change in the rho will make a current for you. So it makes a current for you. So I wanted to find the flux. So the flux of the flowing of flux is equal to the change of the Lewis density minus. Because they have the opposite direction. Huh? When partial derivative of rho decrease, it means that the flow is increasing. If the density inside increases, it means that the flow is decreasing. So I needed that to control this. And look at that. You know the flux. Huh? From the basic physics, you know the flux is like that. Yes? Gauss. Flux of any field is F dot dr, and this is your field. So in your case, you just need to rewrite the F. So if the fluid is flowing from the surface, and if this is the area vector, and if this is the velocity of the fluid, so, and you have a piece of the fluid here, of course, with the density of the rho, I can say that from the Bernoulli equation in the fluid dynamics, I can say that the fluid vector, the flux vector is rho multiplied to V. But this looks like the Newton law, similar to that. Like the electric field. The force, the electric field is a portion of the charge density like that, huh? And the directions. But this is the fluid, not electromagnets. But anyway, you can understand this equation. So we just replace that here. I want to repeat that. I told you I will repeat that for the phase space, phase by phase. And this is the integral over the surface. So it doesn't matter that how many dimensions the surface have. Like phase space 6 and dimensional, 4 dimensional, 2 dimensional. This is a general truth. So we have a theory through Radesky, Gauss divergence theory. You needed to know that this from the mathematical methods of physics or any other place. You know that the V dot dA over the surface is integral of divergence this vector over the volume. I write the volume d cubic x as the volume, just cubic element like the volume. You can write dV or any other things. So I just can use this theorem, Radesky Gauss, and I write it that divergence rho v d cubic x. So this is the total flux is flowing. Huh? If you consider a small element of that with the volume d cubic x, you need just to write this equation with the elements, because this is the flowing flux through the whole volume. You needed to write the volumes. Like the total mass. Total mass is the density multiplied to the volume. Huh? You consider the phenomena of the flowing of the fluid from the surface. So this is a total. Total is total change of what? Anything. The density multiplied to volume. And this is that. Even you can write it in the differential form. And if you want to write the total, really total is the integral of that. Yeah? The total. Like the total mass is integral of the rho. Yes. So, and you can move everything to the right hand side and consider this for any arbitrary volume element. So you get this equation: partial derivative of this plus divergence rho v 0. So the only difference that this phenomenon you always have a good physical intuition about the velocity. The velocity for the fluid or velocity for the electric charge when they're moving, they are just given by the time derivative of the coordinate, x dot y dot and z dot. So this is the definition of the velocity in classical mechanics. In phase space, it will be changed. A little bit will change because instead of the one coordinate, you have one q here and one p here. So if I can be able to change the definition of the velocity, so I can repeat this proof here. I will do this. I will do exactly that. Do you have any question about that? You can read it at this in the book. In the some books of the mathematical physics, you can find it that. Advanced Engineering Mathematics was very good. This is a very good book, Engineering Mathematics. Erwin Percy. I don't know unfortunately I forget the spelling, so Percy. So I have the book, I can show you in my office. So Advanced Engineering Mathematics or any other applied physics books, applied means that applied mathematics book, you can find the proof of that in the better formula with more detail. So, but here you needed to know some supplementary mathematics, is that you need to understand the meaning of the divergence. So I won't spend time to explain you the meaning of the divergence. So this is just given as the total change in the one vector. For example, you have this is the calculation which you needed to do to understand the meaning of the divergence. So you have a vector field, and this vector field is coming to you in 3 dimensions, and you have a box. The element of the box is considered very infinitesimal size, like delta x, delta y, and I want to ask you the total change or total amount of the matter passed from this surface. So when the vector is here and when vector is reached here, so it will be shifted just for that, and also, so you need to go through this book or other books, and you can find the total amount of the matter passed from this cubic, and this total will be proportional to the divergence. So if I want to prove that, so it will take more time. So I want to back to the statistics. So let's go and try to understand the Liouville theorem in general. So we use the same. So we say that we have a conservative phenomena, so that should be given like the divergence of some kind of the rho v. What is this v with double? This is the generalized velocity vector in the phase space. Velocity vector. Phase space. So it should be given like q dot and pair I dot. The derivative not of the x, but also the derivative of the. What is the gradient? Gradient should be the generalized gradient, so should be rho partial derivative of qi, partial derivative of the pi. And don't forget that the rho is a function of qi. So let me to write it that. So sigma I 1, 2, 3 n partial qi rho v qi plus partial dot pair I, rho V I. The velocity vector has a two component, I call it VQI and VPI. The second one doesn't have the meaning of the velocity actually. The first one makes sense about the velocity. The second one is something like the force, the time derivative of the momentum. But we use the same